Okay, on to questions 4 and 5. I should note that although these are useful bits of information, I've stopped asking this type of question on the exam just because we are allowing you to use things like ChatGPT and other LLMs, Google search, and these questions just become a little bit too easy once you have access to those types of tools because they can just answer them for you. So no longer asking these types of knowledge questions, but it's still useful things to know. So let's go through them. So part 4A, explain why it takes 2 instructions to set R0 equals 2009 CO20, but only 1 instruction to set 7C. This is a 32-bit value. This is an 8-bit value, right? And so it takes a move W plus move T to set full 32 bits. Move 32 / LDR are pseudo instructions which generate pseudo, I might have spelled that wrong, insters. So those generate this move W, move T pair. So they're not actually like a real instruction because we can't fit a 32-bit immediate in a 32-bit instruction, right? We need to have some bits for the opcode, so we need to have some space for that. Need space for opcode, right? We need to tell the processor what we want it to do, and we need some space for that. For an 8-bit value, well, we can fit that into a 32-bit instruction, so that's possible. One advantage and one disadvantage of Thumb 2 instructions use both 32-bit and 16-bit instruction lengths. So advantage, the main one here is space saving when 16-bit instruction size is enough. All right, we can just use less space. So why not? Disadvantage, the main one here is that decode becomes a little complicated because we have to now look for both 16-bit and 32-bit instructions. If we just use either 16-bit or 32-bit, then we know that everything we're decoding is definitely going to be that size. So we can always just sort of fetch 16 bits, we can fetch 32 bits, and then decode that same amount. Here we have to choose once we start to decode. On to part 5. We'll do that in this since it's a set of short questions. So which branches would go to the label if NZCV equals 1001? So here we're really just referencing the notes on what these branches mean. So the main one we're going to look at first is the Z bit, right? And that is 0, which means that they are not equal. If we do a comparison, really what we want to think of is like we did a CMP, right? Between R1 and R0, which is R1 minus R0. So what does it mean if we see this here? What do those mean? BMI is negative, and so that N bit is set there. This is the sort of thing that for this type of problem you may be expected to reference the notes for or the manual. So here we can look and see what these codes mean, and we see like MI is N equals 1, EQ and NE are Z equals 1 and Z equals 0. So we're just checking those to see what works. BLT signed less than down here on the page is N is not equal to V. So let's check. We've got N is equal to 1, V is equal to 1. So that's not going to be true, right? BLT doesn't work. BGT is Z equals 0, which is true. And N is equal to V, which is also true. So BGT is going to be fine as well. Okay. On to the next one. If X is a 32-bit number, which bits indicate whether X is 0 or not? And that's going to be all bits of X, right? So we have to look at every single one and say, is that bit 0? If all of the bits are 0, then the whole thing is 0. True, false, using multiple instructions, you could add two 32-bit numbers on the Nucleo board. That's going to be true. right? So if we do something like an add S into an ADC, we can do that type of operation. So we can do sort of arbitrary sized arithmetic if we have larger numbers than what our data size supports. And then finally, the three main stages are fetch, decode, and electrocute. That's false, right? This should be execute. So that's it for those.